In Lab 1 of Physics 2211, we focused on constant velocity. The purpose of this lab is to observe an object at constant velocity. We do this by recording a video of an object moving at constant velocity and uploading it to the program tracker, which will analyze the video and determine the object's position and corresponding time. We can use that data to determine the velocity of the object, which should theoretically remain constant throughout the experiment. We will then compare that data to a computational model, which shows the predicted values for the object's position over time. Important concepts in this experiment are velocity and Newton's first law. Velocity defines the speed and direction of an object in motion. For the velocity to be constant, the net force acting on the object must be zero. This is explained by Newton's first law, which states that an object's state of motion will not change unless there is an unbalanced force acting on it. These are the formulas we are using in the experiment. The formula for the final velocity of an object is the initial velocity plus the net force divided by mass times the change in time. The formula for the final position of an object is the initial position plus the average velocity times the change in time. Since our velocity is theoretically constant, the average velocity will be equal to the initial velocity. This image shows the object we are observing. The system is the object, which is moving on a track, and the surroundings are everything else. We are assuming that air resistance and friction are negligible and thus ignored. As shown by the arrows, the only forces acting on the object in this experiment are gravity and its counteracting force. As they cancel each other out, the net force on the object is zero, and thus the velocity is constant. Here is a video of Tracker analyzing and determining the object's position and corresponding time. We can use the data provided by Tracker to find important data points. Using the first two data points provided by Tracker, we can find the initial position, initial velocity, time interval, and final time. These four data points are needed to create our computational model. Using the starter code provided, we substituted its values with the ones we found using Tracker. We also added our two previously mentioned formulas into the code, which can be seen down below, right here. After running the program in GlowScript, these are the results. Adding the data sets of the observed objects and predicted objects into Excel, we can create and graph the two data sets and compare the two. As you can see, there is a noticeable difference between the two. The deviation of the observed data from the predicted data shows that the observed object has a much higher velocity. This would suggest that the object had a net force acting on it, which means it was not at constant velocity. An explanation for this result would be errors during the experimentation process. When the object first started moving, there could have been a strong force acting on the object. The video quality, which includes variables such as the frame rate, could have also affected the tracking capabilities of the program. There may have also been rounding errors during the calculation, which would have affected the computational model. Here are some further discussions for the experiment. What if the axes were flipped? The magnitude of the position and velocity would remain unchanged. However, the direction of both would be changed from a positive value to a negative. Is it possible to determine the forces that cause the net force to be zero? As seen previously, the only forces that we know for certain are gravity and its counteracting force. It would be unlikely for us to be able to accurately determine the other forces present.